Have you ever just stopped and wondered how we can possibly measure something as insanely complex as the human eye? I mean, how do we design glasses or contacts for a system that has dozens of unique moving parts? Well, the answer, it turns out, is to create a blueprint, a simplified model called a schematic eye. So let's dive in and see how scientists turn all of this messy biology into elegant, predictable physics. All right, here's our game plan. First, we're going to tackle just how incredibly complex the eye is. Then, we'll see how schematic eyes act as a simple blueprint. We'll level up through a few different models, see how they literally define what 20/20 vision is, and then we'll finish with a really surprising truth about our own perfectly imperfect sight. So, let's kick things off with the core problem we're trying to solve, the eye itself. I mean, just look at this thing. It is an absolute marvel of engineering. You've got the cornea at the front, bending light. You've got a flexible lens right behind it that's constantly adjusting focus. And then the retina at the back acting like a super high-res sensor. All of these parts have their own unique curves, their own properties. It's a living, breathing optical instrument. And that brings us to the million-dollar question, right? How on earth do you take this beautiful biological mess and turn it into predictable math? How do you create a standard when every single person's eye is a little bit different? Well, the solution is to build a blueprint, and that blueprint is called a schematic eye. Okay, so a schematic eye isn't a real eye you can hold. It's a mathematical model. Think of it like a master blueprint for the human eye, created by averaging the measurements from thousands and thousands of real eyes. It totally simplifies the biology into basic optics so we can finally work with it. So why is this so useful? Well, for one, it lets us model how light should focus perfectly on the retina. It also helps us understand what's going on when it doesn't, which leads to things like nearsightedness and farsightedness. And maybe most importantly, it creates a universal standard, a common language. So every optometrist in the world is working from the same basic blueprint. But, not all blueprints are created equal. We're going to start with the simplest one of all, the Emsley Reduced eye. You can think of this one like a quick sketch on the back of a napkin. So this is it, the Emsley Reduced eye. Now, I know this diagram might look a little complicated, but its true genius is in its radical simplicity. It basically ignores all the messy biological details and makes a few really bold assumptions to get to the absolute core of how we see. And here's the biggest simplification of them all. It pretends the cornea and the lens are just one single surface. Yep, all the complex light bending that happens in a real eye gets condensed down into this one imaginary plane. And that single imaginary surface, it's given one power value, plus 60 diopters. Now, a diopter is just a unit that measures focusing power, kind of like horsepower for an engine. So that plus 60 represents the total focusing strength of an average eye, all wrapped up in one clean, elegant number. So the Emsley model is simple, it's elegant, and it is fantastic for answering really fundamental questions about vision. But to get more accurate, we need to start adding some of that complexity back in. And this is where we level up. We're about to go from that simple sketch to something more like a detailed architectural blueprint, and then eventually a full-blown 3D render. And this visual just shows that jump perfectly. On the bottom, that's our simple Emsley sketch. But on the top, that's the Gullstrand No. 2 Simplified eye. You can see right away it's way more realistic because it actually separates the cornea and the lens, treating them as two distinct parts. This table sums up the progression beautifully. We go from the Emsley, our simple sketch with one surface, to the Gullstrand No. 2, our architectural blueprint with 3 surfaces. This one is basically the industry standard. And then we level up one more time to the Gullstrand No. 1 Exact eye, our photorealistic 3D render, which has 6 surfaces. Now, this most advanced model, the 3D render, it has a kind of superpower. Because it includes all the internal details of the lens, it can actually simulate the physical act of focusing. And here it is in action. On the left, the model shows the lens in its relaxed, flatter state for seeing things far away. But on the right, look at that. It shows the lens getting thicker and more curved to focus on something up close. That's a process called accommodation, and it's a huge leap in how accurately we can model what our eyes are doing. Okay, so we have these incredibly detailed models. They're cool, they're complex, but why does any of this matter to you? Well, it's how we define something we have all heard of. 20/20 vision. Here's the most crucial point. These schematic eyes provide the mathematical bridge. They let us connect a specific sized letter on an eye chart 20 feet away to the exact size of the image that letter should form on a perfectly healthy retina. So here's the breakdown. You start with that standard letter E on the eye chart. From 20 feet away, that letter creates a very specific, tiny angle as the light enters your eye. We then plug that precise angle into the schematic eyes formula, and the math tells us exactly how big the image on your retina should be. And here's the answer. The image of a 20/20 letter on your retina is just 24 microns across. That's 24 times millionths of a meter. It is an unbelievably small and precise target that these models allow us to define. It's just amazing. But wait, there is one final fascinating twist to this whole story. Because these models, they're perfect, but our eyes, they're not. You see, there's a catch. All of these beautiful, elegant models, Emsley, Gullstrand, the whole shebang, they are all built on one fundamental assumption, that all the optical parts of the eye are perfectly centered on a single straight axis. But the truth is, our eyes aren't perfect. The different parts are actually slightly misaligned. The geometric center of your eye, the center of your pupil, and the actual line of sight you use for your absolute sharpest vision, they don't line up. They're all just a little bit offset from each other. So what these models give us is a perfect blueprint for a beautifully, functionally imperfect system. Our eyes are flawed by design. And it really leaves you with a final thought, doesn't it? If the very instrument we use to see the world isn't perfectly aligned, what else don't we see perfectly?